I don't know whether the type of matching search theory to analysis Weiler index theory, but that's certainly the idea, as I already told you. Yes. Told you last time. So we need to know index theory, and this index theory, way I'm thinking of it, uses C-star algebra, that's also coming up last time. Decay theory, and then index theory of operators, like the signature operator, in this context. So, as we need it, I guess we should talk a little bit about it. And the first thing to do is a quick definition of C-star algebras. So who does not know C-star algebra is? Everybody what it does? What is it?
Yes, it's a complex algebra with star, with norm, and satisfy the system.
The quickest way to get it is to say a closed star subalgebra A of the bound operators on the Hilbert space. Okay, and the Hilbert space has a norm that makes it clear what closed means. It's an algebra by composition, addition, and it has a star, the adjoint, that's what the star is. And everything isomorphic to that with the same structures, norm, and so on, is also called C-star algebra. But for us, indeed, all the C-star algebras we're going to work with come up as subalgebras of bound operators on the Hilbert spaces anyway, so it's very convenient to use that. Let's look at examples. Use that a little bit. An obvious example which fits into that is the compact operators on a Hilbert space, or K, is a C-star algebra. And just to remind you what this is, these are all bound operators, which are compact in the sense we saw last time. The T of uniform closure is compact. But another convenient way to describe that would be to say we take the T which have finite rank, finite image, and then take the norm closure inside the bound operators. And actually that's the way to make C-star algebras if you're not so sure about this closedness property. You just take your subalgebra and close that. You do that a lot of times during these lectures. Also. So that's an ideal two-sided ideal in all bound operators on the Hilbert space, which is a nice thing to know. Another one, function algebras, continuous functions on spaces, like continuous functions on a real line. Make that right. Let's take continuous functions. The zero means vanishing at infinity, so going to zero as t goes to plus or minus infinity. That's also a C-star algebra, acting, for example, on L2 functions, continuously the same way.
So what do you mean by that? That they have compact support, or just that they tend to zero?
They tend to zero.
Okay.
Otherwise, you would be in that situation. Compact support isn't quite closed. If you take a closure, you will get all things which tend to zero. Okay. So let's say that contains C. The continuous function with compact support on R, and it's equal if you close. And another example, which is kind of secret, is going to come up if gamma is a discrete group. We can make the Hilbert space of L2 functions on gamma. Formal linear combinations of group elements with the coefficients are ensemble, and those are the Hilbert space, so there are all the bound operators on it, and inside that we can find the complex group algebra acting. A group element acts by shifting around the group elements, and close that up and define that to be a reduced C-star algebra of the group bound. Right, so you see they all come up as subalgebras of the bound operators on the Hilbert space. The Hilbert space might depend on the situation. So, well, that's C-star algebras. That's K-theory. I'll define it in a second way a bit later, but let me do it traditionally. So K-theory for C-star algebras is actually not a very long story. If you want to define it, it's just two groups. There's K0 of A, and this is defined as you define K0 of any ring. C-star algebra is in particular a ring, and what we define K0 of a ring? Now, upwards? I don't know. Maybe you
Take the monoid of all isomorphism classes of finitely generated projective A modules and take the Grothendieck group of that.
Right. So, some Grothendieck group of a semi-group of generated projective modules, and being a projective module, you're the image of a projector, and so we can also say it's the semi-group of projectors in matrices over A, which you can sum by doing direct sum, making the K bigger, and then make the Grothendieck group of this same. Very well. So to make an element in K0, we have to find a projective module or projector. So later on you do define indices as elements in K groups. So now we know what we have to do. We have to find projectors. K1. Those two guys are chatting, so we can ask them. Do you know what K1 is?
No.
No. Do you?
Take the automorphisms and
Right. So and so we will say we can take invertibles in NK of A. Those can also be stacked together by block sum, making the K bigger, and that defines a semigroup, and we take the road decomposition of those. So, message about K1. If you want to make a K1 element, you find some invertible element in A1 matrix algebra. So again, to make elements, write down indices, we know the blueprint now a little bit. Okay. And just as an example, zero of compact operators in the Hilbert space, two is Z generated by any rank 1 vector.
So for K1, don't you have to take pi 0?
Yeah.
So I will just wait here to make a precise definition in a second.
I think you don't need the Grothendieck group, right? Because it's
So the inverse is given by the inverse operator, the inverse invertible matrix element. That And now we write down one of the big facts, which is highly non-trivial to write, which is given a short exact sequence of C-star algebras. So we have, as in the case before, an ideal in a C-star algebra A, and there's quotient C-star algebra Q. Then we get a long exact sequence of K groups. Everybody has seen this, and in this case it's a 6-term cyclic one. So K-theory is a function, so the maps in the algebras induce maps between the C-star algebras that will be the K-theory groups, and there are two boundary maps from K1 of the quotient to K0 of the ideal, and the other way around, which make this a exact sequence altogether. And there are good reasons to call these maps, well, maybe we'll call these maps index maps. See that a bit later. So that's a very important basic input of K-theory C-star algebras, which we going to use all the time, just in a bit. And so maybe as just a baby case of index of signature operators. Well, looking at this diagram, you want to find the index of the signature operator in these K-theoretic terms. We should produce something in some K1 of a quotient, and then get K0 of the ideal, and that would be the index of whatever we define. And luckily, the signature operator, so on N or K, closed, smooth, oriented. Manifold, we do have a signature operator, right? We defined it last time. So that is, by definition, an operator on the L2 forms, L2 differential forms. So we're almost there. We have to get some elements in bounded operators on a Hilbert space, and there it is. But there's a little problem because I also discussed last time that it's not a bounded operator. That's not such a big deal because, and that's exactly the reason why I introduced this functional calculus. The functional calculus allows to make bounded operators out of the unbounded when we start. So we know that chi, the signature operator, is element in bounded operators on L2 of the forms for any bounded function chi, and the bounded function chi I want to use is a function like that. So here's the real axis, and there's t, and here's chi of t. It approaches plus minus 1 as t goes to plus minus infinity, and should be off. Minus 2 minus t, divided tends to 1. Okay. But we could use many other functions, but this has the effect of taking the spectrum of the Dirac operator, which has obviously large entries. That case is actually really the spectrum consists of eigenvalues, they're very big eigenvalues, and the big eigenvalues are just made to be a little bit less than 1. And the very small one, the negative ones, the large absolute value, are made to be just a bit close to -1. So we don't change the great, okay, we change the great picture, but just the unboundedness is pushed to be bounded. That's somehow the idea of these functions. You might also recall that the function of an operator, in such a case, we have an eigenvalue, you have just the same eigenspace, but this chi of d acts by multiplication with chi of the eigenvalue on this eigenspace. So that's the whole idea. Very well. Now, why I insist in this function to be odd, that's a little consequence of the properties of the functional calculus. This implies that chi of the signature operator is also odd for this tau, this grading, which is the important extra bit in the signature operator. Okay. If the operator is odd and the function is odd, then chi of the function is still odd. So anticommutes with tau. Odd for tau. Which means, and that's a little detail which unfortunately is necessary to take into account, but it means its oddness that chi of d actually looks in our decomposition of the L2 functions into the even part and the odd part for the tau grading. It's an odd operator, so it's off diagonal. It has some plus part to it, and d being self-adjoint, chi being real valued, chi of d is also self-adjoint, so that has just to be the adjoint of this operator. And now I make the unitary operator. We need to produce a K1 element out of this picture. We choose a unitary U between the form, the plus part of the forms and the minus part of the forms for our signature grading. These are both infinite dimensional Hilbert spaces, so we can certainly do that. And there's a choice to be done, but the unitary group is contracted, so it's an insignificant choice. That's an ugly part of it. I would like to get rid of it for this presentation here. We have to do this to get the right answer. And then we consider chi of the plus part of it. So that goes from L2 plus to L2 minus, and I can compose with U star, and that's a self map of L2 omega plus. Okay. Bounded operator L2 plus, and I claim that is U star plus is actually what we want. We want something representing a K1 plus. We want an invertible element is invertible, but not quite. It's invertible if we push it forward to the quotient by the ideal of compound operators. Okay. Which is even better because I wanted to put myself into a situation where I have this available, to have the index map available. So even better if it's in a quotient, some situation like that. Now, prove that is, should I do it? Nice. So when you multiply this with its adjoint, so it's actually a unitary modulo complex, you will end up with checking chi of d squared. You have to look at the operator chi of d squared. Now that is chi squared of d, by the properties of functional calculus. And let's look at this function chi squared. You can certainly see that it goes to plus 1 as we go to plus and minus infinity. So it's making sense to compare that with 1. And then we see this is f of t. Right? F is the difference between 1 and chi squared, where f is our leading function in continuous functions on the real line, which vanish at infinity. That's just the whole point of picking chi, such that chi squared is equals to 1 plus minus infinity. And from that, you see that this is not an arbitrary operator, but it's one of those which you get when applying a very special function to D. And that, so my claim is that this is compact. So then we're done. So we saw that the operator composed with its adjoint gives us the identity up to the narrow compact operators. You have to look at the plus part, it takes care of itself very easily. And this compactness now is a consequence of the Relish theorem and elliptic regularity. So minus du, if we do, let me just write L2, then we apply f of t, and we end up in L2 again, bound operator. I'd like to see that this is a compact operator. Now there's one thing we can do, which is apply f of t and then t. This corresponds to this composition. This corresponds to t times f of t, and take this function and substitute t for t. And this is still a bounded function on R as it goes to 0 for infinity, at least if you make the choice of f and chi appropriately, which you can. So this function is still a bounded function on R. So this is still a bounded operator to L2. By elliptic regularity, this means that our f of t itself goes to the first Sobolev space W1. And actually the way I define W1 is really composed with D, and then if it's then still a map which is bound from L2 to L2, then it's a map which is continuous to W1. Okay? So we can write our f of D actually as f of D as a map from L2 to W1, composed with the inclusion of W1 into L2. Just elliptic regularity used here. And now we're done. So this is still bounded for the norms on L2 and on W1. And this here was a compact map. Take the unit ball as a scaled unit ball image. It has a compact image on the second map, so the whole thing has a compact image, which is what we have to prove. So, why? The answer is this picture. This picture we see f of b is the composition of bound and compact, and therefore is compact. And this means we get the class, we call this the signature function class of M inside K1 bound operators on L2 modulo compact operators. And by the principle of this diagram, we can define the index of the signature operator, that's now a definition, as the image under this map, on this boundary graph, to K0 of the compact operators. Okay. So that would be the abstract way to define an index of an operator. We somehow, up to some maneuvering, we use this chi of t, produce an element in a C-star algebra, which is invertible, modulo some ideal. And then you apply the index map, the boundary map of the non-exact sequence, the term exact sequence, and you define the index to be the image of this map. Define this. define this guy here by this. Now I told you before that K0 is isomorphic harmonically, the n type is Z, and of course this is the index we discussed last time, the difference of the positive part of the kernel, its dimension, and dimension of negative part of the kernel, which is then something we have to prove. I mean, could work it out, but let's stop here. I want to take this principle as the take-home message. Here, this index is equal to the dimension of the plus part minus the dimension of the kernel. Okay, so it's not so clever. Right. Now, K-theory has more or less built-in homotopy invariance properties. For example, we made choices along the way. And one which is most obvious is this chi choice and was a U choice. As long as you homotop these choices so that you always stay within the class of things which give you K-theory elements, so you have to make sure that this remains invertible modulo K throughout, then you don't change the K-theory class. Okay? So built-in homotopy invariance, and that was corrected by Ulrich, but I have to write it down in the definition, so it could have written down in the definition of the K0 group as well, homotopy class of projectors. It's been perfectly okay. So it's built in, and e.g. this implies independence of the choice of chi and u in our construction. And throughout we have a lot of choices. So for instance, we also choose the Riemann metric to make the signature operator, but again you can deform the metric as a homotopy and you will get the same class here and also then the same index class here. So that all follows from the homotopy invariance properties. And now let's make a hypothetical application of this, which I will make real a bit later. Assume that the spectrum of the signature operator would not contain zero. That's never happening on a compact manifold, so that's why it's hypothetical. But let's assume it would happen. Then it actually doesn't contain a whole interval around zero, because the spectrum is a closed set. And we can choose chi identical to 1 on epsilon infinity and identical to -1 on the other side. And so my function would not look like that, but would really look like this. And another aspect of the spectral theorem is that it's only feeding, the function chi is only feeding the spectrum of the operator. So here, because there's an absence in the part where the function goes from -1 to +1, we can kind of ignore that. Particularly if you compute chi squared, it's chi squared of d is the same as 1, because this part where the function goes down to 0 doesn't feel anything because it's away from the spectrum. So that implies chi squared of d is equal to 1, no error. which, if you look at our construction up here, means that the class which we define here actually made sense already, one to the left. Okay? So, with this hypothetical assumption, we have depending on this particular property, which isn't stable under changing metrics or things, you can't guarantee that it's stable under those, you would have a lift given of this class to the left. Okay? Class which I control of the signature lift depends on 0 naught in the spectrum of the, and is therefore something subtle. And you don't know what happens with lift if you change the metric and maybe you have another situation where you don't have 0 in the spectrum, or things like that. Okay? Now this is a doubly hypothetical set because we can compute K1 of all bundle operators at 0 anyway, so that is not most exciting to find this lift. However, I just wanted to point out this general pattern, which one of many different ways to do it, but one which I like and which I think is very natural and successful to do index theory using C-star algebras, these operator algebras, is so. Let's say general pattern. For some kind of K theory index of something like this signature operator, we identify suitable algebra, which depends on your situation. So remember that I talked about saying we have M, but we might pass through universal coupling, non-compact manifold, that has a signature operator of its own. So we might try to work with this thing. Suitable C-star algebra, depending on the situation. We call it some B-star, which contains the kind of the operator we care about. Right? We saw that this is something we want to know, and we should also identify an ideal unit, C-star, and clearly the C-star should play the role of the compact operators, so we want chi squared congruent to 1 modulo ideal. Okay. And then the whole machine works, and we can define machine will give us a class of M in K1, I don't know, of E star mod C star. And actually, if you take further symmetries and so on into account, it typically will be 1 plus the dimension of the manifold which you get. So recall these are only 2. This we always have to think of as mod 2. So there are 2 different versions coming up here. And then you will have, of course, by the same principle, an index map to the Km of the ideal C star, and this class of M and the signature operator will be sent to some version of the index of the signature operator living in the K-theory of the ideal algebra we identified. And hopefully we can say something about this, like as the integers for the combined operators. That could be much more interesting if you're lucky. So that would be part one of this picture. And moreover, if some geometric reason implies that already chi squared of t is equal to 1, some invertibility property of the operator, we can use this lift. Typically that's really a geometric reason, some particular choice of metric or extra datum, which will allow us to do this lift. And this lift would then be a row class, depending on all the geometric data. So I'm writing the full operator here, which is living in Kn+1 of the algebra B star. And if you're a bit more lucky than in the easy case of a compact manifold, this might be some group which is non-zero, and they can read off information about the geometric reasons for the invertibility of the operator. Okay? So that's the general picture, and now we have to think of situations where you can put this to work, different from the situation I just described.
But this row class is more interesting than only saying that the index of this operator is zero. I mean, it's really
Right.
interesting.
I mean, this is the principle we all know and love. We don't want to show that something is zero. That's a good thing to know, but typically you want to find a good reason why it is zero in terms of the secondary invariant. So topologists have done this throughout the history of topology, I guess. Not only be satisfied with the vanishing result, but use it to produce a secondary invariant which tells you something about the situation, why something vanishes. So it's exactly in this spirit that I try to set up primary and secondary index theory rather than this K-theory C star. Now, let me give you a full-fledged definition of K-theory, which I found in lecture notes by Hickson and Günther and Hickson. So an alternative and now a correct, full definition of K-theory, which and actually we will produce a spectrum in the sense of homotopy theory separately. So for that we need an extra bit of information. Grading on a C-star algebra A just means we split A into a 0 part and a 1 part to close subspaces, and we have a usual multiplication rule in these subspaces by the addition, and A0 times or AI times AJ multiplies into a I plus J, and both parts are preserved by the star. Okay. So this one example, C0 of reals is C2 graded by the direct sum of even functions and odd functions. And now comes my the real definition, which point needs up. I make a space, give given A actually could be C2 graded. This algebra A. We define K of A to be a space of mappings, as we have seen in last talk, or first talk, the Oscar. Now, these mappings are homomorphisms of these algebras defined. So they go from target. The source algebra is this C0 function from R, and the target is our algebra A, but we have to enlarge it a little bit to have room enough, and we tensor with 2 by 2 matrices over the compact operators. So you can think of this. So that's also graded with the diagonal matrices being even, the off-diagonal matrices being off. And this is the graded tensor product, which just means if you multiply together and you exchange factors, you get the minus sign if both terms are off. So the way we're used to define such multiplications, for instance, of chain complexes. So that should be grading disturbing. C-star homomorphism. Both are C-star algebras, so I can talk about the C-star algebra homomorphisms. That means to each F I get an element in here and it's a homomorphism. Now that's as a set, and it gets a topology with pointwise convergence. So I have a net of phi i's. This converges to some phi if phi I of f converges to phi of f for every element in the source. That gives me a topological space of star homomorphisms, and the definition of K-theory, Kn of A, is defined to be phi n of A, where the base point is the zero homomorphism, which is of course also homomorphism with C-star algebras. They're not unit preserving. This isn't a unit algebra. It's not necessarily unit preserving. None of them. So, there you go. And another fact is, well, there's two facts. One of them is that K of A actually is in a canonical way an infinite loop space that relies heavily on quadriplicity. So in that sense, I really take a spectrum, I take the model of a spectrum here, and the second one I wanted to write is that the six-term exact sequence, which you see pieces of here and there, I guess.
So could you make the infinite loop structure by acting the linear isometries operator of the Hilbert space, which defines K, things like that? Would it be possible?
Well, I guess you either get the homotopy in the second loop space, the string, and the loop space itself, and that's, I don't know, it's just the quadriplicity map. If you think of a pi second loop spaces, these are maps from S2 into that, so you can put the S2 thing into the other side, and you have to map to A tensor C2 as functions on R2, and then you're pretty close to standard ways of writing down quadriplicity. I guess that's what you wanted to do as well, right? Didn't quite catch your suggestion.
Well, the space is an E-infinity space because the linear isometries of linear isometries operator of the Hilbert space acting on the M2K factor.
And I mean, somehow should be hidden at some point the use of the bot element one way or the other. Is this hidden in your infinity structure?
No, it's not him. It's, I mean, let's discuss it.
Okay, so, yeah. Second fact is that given an extension, as we had before,
In this language, can you explicitly write down if you have a projected module, let's say,
I'll get to that in a second. So, tell two force and hard facts and then do a little example. K-theory is homotopy groups of a certain space. We want to get a long exact sequence of these homotopy groups for a certain short exact sequence of algebras. Where should that come from? Of course, from a vibration. Right? And that works in such a situation, actually on and off, without wiggling and doing homotopy, whatever, we get a vibration of associated spaces K of the algebra. I guess it's even locally trivial fiber one. As good as it could be, and which induces the long exact sequence in K-theory. Using this dot periodicity, which also gives the infinite loop space structure. The second loop space of these is with the canonical homotopy equivalence to the K of A itself, so that we really don't have more than two groups up to the isomorphism induced by this homotopy equivalence. And that's going getting into the infinite loop space. So, where are we? Right. We want to see examples. This works with gradings if we get an isomorphism from A0 of A traditional to I0 of this space of homomorphisms from the C0 of R to A, hence the 2x2 matrices or compact operators. Well, how do we do that? Recall that proton deconstruction means you take two projectors and take their formal difference. These are matrices, finite matrices over A, which are projectors, and we can make them self-adjoint projectors. If you want, that's no problem in C-star algebra work. So this is equal to P star and P squared. Q the same. Okay. What is the homomorphism whose component we pick here? So we have to take the function f in C0 star, and we have to assign to that in a homomorphic way an element of A tensor 2x2 matrices over the compact operators. And the way you do that is to write down P to fill up with zeros and Q to fill up with zeros. So, and each of those you should think of as sitting in A tensor, actually finite matrices sitting in compact operators on the blue edge. Okay? Now, that's not using F yet. I have to multiply F of 0 with this matrix. And that's, of course, still an element in this algebra. And you see this is certainly homomorphic because evaluation at 0 is a homomorphism. And this is a projector. And it's also parity preserving. If you have an odd function, f of 0 is 0, so the fact that this looks very even doesn't work. So that's okay, and that is, you might check an isomorphism between these two groups. So it might be an interesting exercise to check this for the compact operators themselves, so for the complex numbers. They should get the V out of. So you have to think about why this pattern where we have P, comma P here, which is 0 in the broken D group, is homotopy to the 0 map. So an exercise to work this out. It is doable. You have to think that these exercises. And give you a more sophisticated example. Given the signature operator and this algebra P star with the ideal C star as before. So I of this operator is C star for the functions chi we're using, and f of P is C star for these vanishing at 0 functions we're using. Define chain. Well, you know that in such a situation, you can define the index of the signature operator as an element in K0 of C star. Right. So just recall this is phi 0 of this maps from the functions on R to C star tensor n2 of K. Right? So once again, I have to write down a homomorphism from functions on R to the algebra C star blown up by these matrices, this compact operator matrices, and we obtain this index here as the homomorphism sending f to f. So actually it's not really important to look at this n2 part here. Right? Function typus tells us, so this is precisely a homomorphism of C star algebras, and we actually will have this property of being an odd operator we discussed already. An odd function is sent to an odd operator, so it's really a degree preserving homomorphism, exactly the kind of thing we want, and it's something that of course we have to check that the traditional definition is completely the same as this kind of definition from this homomorphism.
Is it FD tensor the identity matrix on N2K, or is it? I mean, f of D
Well,
is.
there's no identity matrix in here, so you have to take a rank 1 thing in a block.
You take rank 1. So it's a rank 1 projector in each of the diagonal entries.
No, only in the top one.
Only in one.
Otherwise it would be 0. The 2 can be cancelled. No, that's what you do. Right? And it turns out that this point of view is for quite a few functions, because it has this natural feature in it, quite a convenient point of view. And I decided to present it, although later on we will not talk about that too much, because I felt all those which know K-theory well maybe are interested in seeing a slightly less standard approach to it, which might be useful for some purposes. So I have to mention that Ruby Zeitler uses this picture, and also Gründner and Dixon to get kind of unified approach to index theory for all dimensions. So this uses another feature, which is when we want to describe, instead of K0, Km, I indicated that the index should live in the K-theory degree, being the dimension of the manifold. This looks now like we have to construct not a single operator like that, a single homomorphism, but something involving a whole M sphere of operators, an element in pi m. But we can trade this pi m, this sphere part, to using Clifford M symmetries instead. That's again involving quadricity and some of these features. So instead of looking at this picture the way I described it, you also observe that everything has extra Clifford M symmetry, linearity in it, and you kind of automatically get the element defining something in Km. So it's a very uniform point of view which just works without extra work, observing that we can take the signature operator having this Clifford linearity built in. So that's one point of view. And the second one is that we can describe easily the theory multiplication properties with this picture. So things where this picture is particularly useful, I wanted to mention. Right. Now,
I think that product then uses the co-algebra structure of the
so zero product using a co-algebra structure which you can build into this homomorphism picture without too much work. Still have a couple of minutes, and I don't know if I won't define the relevant C-star algebra today, but show you in this picture we just here only defined the index itself. But I told you, together with the index, which lives in K, we use extra symmetries, Km of the analytic C-star, it actually should come with, here we have the index of the signature operator, and there it is, it's just a homomorphism, and its class. It should come with a class, let me write in the K1 of T star mod C star, and this should be related to the fact that if we map further to K0 of T star, our index element must be mapped to 0. Otherwise it won't have an inverse image here by the exactness of the sequence. So yeah, how can I complete this picture in this homomorphism picture? And that is maybe instructive to see here. So this was the class mapping F to F of D, and the homotopy class of these homomorphisms, or the component of these homomorphisms, is then my element in K0 equal pi 0. If I map it further, it's of course just thinking of this as composing with the inclusion map of C star to D star to get a homomorphism F maps to F of D, but now we think of this as sitting in D star. Here it was sitting in C star. Why is this suddenly homotopic to the 0 homomorphism? That's of course the big question. Here it's not, otherwise this index construction would be boring, not in general, but here it should be, and this is actually not so hard to see. So this is our phi. I want to write down a family phi t of such homomorphisms in the following way. I complete the real line by adding point minus infinity and then point plus infinity, and now I can shift this to t plus infinity with a homomorphism alpha t. Okay, no problem. This is certainly homomorphic, so there's no big deal. And phi t I define to be f descend to f of alpha t of the Dirac operator. Now what is happening if I do that? I take this, I shift it, and then I compose with f. This is going to be a function which doesn't have the value 0 at minus infinity, but it has the value f of t at minus infinity, this composition. Right? So instead of going to 0, it's only bounded, not any better. That wouldn't be permitted. I mean, this function of d will not lie in C star, but it will lie in D star, because bounded functions which have a value of plus infinity are perfectly okay, and we end up with an element still in D star. Okay? So that is still by our assumption on how we make this D star algebras in D star, because it's a bounded function on this thing. And now, what is happening if we let go t to plus infinity? Well, eventually each function f kind of shifted away, and we will just converge to 0. On the other hand, if we let go t to minus infinity, so we just do the identity map, so t to minus infinity, so this is just going to be f of t. And you see the required homotopy between our homomorphism and the zero homomorphism just built in by shifting the argument. So it's a very beautiful natural construction we can do. And actually you see what this is. This is in D star, not D star, a loop from 0, because that's 0 in D star not 0, to 0. Which means not only is this a reason why the image here is 0, but even better, it gives me the class in K1, which is I1. This is just this IT loop of homomorphisms from 0 to 0, we want out C star. Okay, and that's actually also how the index map is working. Lift the loop to this and evaluate at the endpoint, and we get the boundary map. Well, I guess it's high time to stop here, but you can see exactly how these, this new point of view actually very beautifully works. Topologists should like this kind of construction. Questions?
Isn't it the grading on the algebra C naught R important? And the grade is what I understood from your remarks that you can't just. I mean, this deformation, if you shift the function to plus infinity, if it was an odd function, it certainly doesn't stay odd during the.
Gosh. I have to admit that I worked this out this morning, and
Maybe it's better to cut the function into two pieces and shift it symmetrically. But this seems somehow to destroy the grading.
I have to think about it. I mean, there must be a canonical way to get the loop. Maybe that was a bit superficial. So let's say there might be some details we worked out, changes we made, and exercises to what is working is if you have a gap around 0 in the spectrum, then you can do the shift you described to get the reason why the index is 0 already in here. just scale. But, the other one, yeah, I'm not positive. You're right. It's too brutal and destroyed the gradient, which is an important piece in the whole story. Yeah. So take this last remark.
Or is this, if you have the other grading, does it become Ka minus 1?
You're right. You really have a point. There is something you have to think about.